viewing the lectures anymore on Blackboard? Not yet? Okay. I guess quiz 1 is coming up next week. So that probably will get you started on viewing the lectures and the lecture notes and all that. But what we'll do today is go over uh, the material that I had started last time um, and pretty much finish out the handout that I gave you last lecture. So basically, what we were talking about last time was this new topic of calculating deflections of structures using energy method. And I told you last time that essentially what the energy method relies upon is the fact that any structure, if you do external work on that structure, it deflects. And as it deflects, it kind of behaves like a spring as a whole, and it stores energy within itself. So I was giving you this simple example of this undeformed spring. You apply a load and it deflects by this much. And if you apply the load very slowly and you plot the applied load versus the deflected amount, then you will see that for linear elastic structures, the applied load kind of varies linearly with the deflection. Make sense? If I, for example, I have this column here, and if I apply transverse load to it at the top, the more load I apply, the more it will deflect. If I apply P, it deflects by delta. If I apply 2P, it deflects by 2 delta. So that's how linear elastic structures respond. And we went through this argument of, as I apply this load, how much energy is stored. And this is a very important concept that you have to make sure you understand. So let me ask you this. I have this structure, and if I apply a force here slowly, force P, up until the final point when it reaches P and the deflection is delta, then what is the total work that I am doing on the structure by applying this force P slowly so that it reaches an amount delta? What is the external work that I am doing on the structure? P delta would have been fine because I guess force times distance is what you're thinking. It would have been fine if I had applied a constant P throughout its deflection. Right? I'm not applying a constant P. I'm slowly increasing, starting from 0, I'm slowly increasing and reaching the final value delta. Because as you said, I think last time, if I apply a total P initially, then it would just deflect back and forth. Just like in a spring, if I hang a mass from a spring suddenly, it would bounce up and down. So we are not doing that. We are applying loads very, very slowly. That's why I had plot this applied load versus the deflection. We are climbing up this curve very slowly up to the value where load is P and displacement is delta. And I think last time we showed that it is actually area under the triangle, area of this triangle, that is the external work done. P delta would have been area of this rectangle. But we are not really applying a total force P up here at the starting. We are applying force slowly as it climbs up. So the total work, external work done will always have that half in there. Make sense? For static problems that are loaded slowly, that half will always be there. Half times P times delta. That's the external work done on any structure. And I had also told you about how structures in general store internal energy. So for example, I was telling you about this truss that I'm loading with 2 point loads, P1 and P2. And no matter which order I apply the loads, I could apply them together slowly, or P1 and then P2, or P2 and then P1, or whichever way you choose. It does not matter which way you apply the load. What path you take to get to the final deformation does not matter. And that path independence is basically what defines a conservative system. So when we apply these loads, these are external loads. When P1 will do some work as the point of application moves from here to here. P2 will do some work as it moves from here to here. And that total external work done would be this guy. P1 times delta D1 integrated from 0 to delta 1, and P2 times delta D2 from delta T2. And I showed you last time that if you load them simultaneously, then you would be again climbing up this curve of P1 versus delta 1 and P2 versus delta 2 along the blue lines. So even in that case, the total external work done would always be half P1 delta 1 plus half P2 delta 2, no matter which order you finally end up with there. Okay. And as these two P1 and P2 external loads do work on the structure is going to store energy within itself. Just like I was doing to this column. This column, I apply a load P, and in this bent configuration, in this deformed configuration, it is storing a lot of energy, right? It's like it's behaving like a spring. As soon as I leave it, it kind of wobbles back and forth. So in its deformed configuration, this structure has stored a lot of energy within itself. And for trusses, I showed you last time that if you think of each member of the truss as a single spring, can we do that? Can I think of each member of a truss as a spring? Why or why not? What?
Yeah, you can, because it's elastic material and you know that it's applied under tension.
Okay, yeah. So if for trusses, especially, each member is either in compression or in tension, right? So truss members don't have any bending in them. Truss members have compression or tension. That's exactly what a spring has. If I have a spring, I can either compress it or pull it apart in tension. So you can think of this truss as a structure made up of how many? 7 springs. So each one of those elements, each one of those truss members is acting like a spring, either in tension or in compression. And we have just said that the energy stored in a spring member is half times K times delta square, or half times the load in the member, load in the spring, times delta. So when the external loads P1 and P2 act on the structure, each one of those internal members deform, either in compression or in tension. And when they deform, they store energy within them, just like a spring would. And what is that energy? You can calculate that energy by doing the exact same thing that we did for the spring. Half times the force in the member times the deflection in the member. Half times N times delta. And if you sum that up over all of those 7 members, then that would be the total internal energy stored within the truss. And this concept works for any structure that is linear elastic and conservative system. Right? Pick whatever structure you want, a big building, a bridge, a dam, or whatever. If you apply load on that structure, then during the process of load application, you would be doing some work. You would be doing some external work. That external work would be half times E times delta. And as you do that external work, the structure would deform. It would deflect a little bit. And as it deflects, it would store internal energy within itself. For the truss, it stores internal energy among all of its members. And if I total up if I sum up the internal energy among all of its members, then that would give me the total internal energy stored in the structure. When I remove these two loads P1 and P2, the structure would come back and return that energy stored within itself. And that's what the conservation of energy principle says, that external work done on a structure would be equal to the internal energy stored. Okay. I'll also write out here that this is equal to sum over all the elements M in the truss. By the way, do you understand this notation? M is just a member of the truss. So for this particular truss, there are 7 members. So M going from 1 to 7 and half Nm delta is what I'm talking about. So I'll replace N here with the stiffness of the truss member, half times K M times delta square. or delta M square. They are both equivalent expressions of internal energy stored in the structure. Right? It's not a terribly complicated concept, but you need to make sure that you understand or try to relate it to something simple, something as simple as this. External work done, internal energy stored. Same thing works for this structure also. External work done, internal energy stored. And no matter how complicated a structure you have, this will always work. External work done would be equal to internal energy stored as long as it is linear elastic and a conservative system. Okay? Any questions on this concept, first of all? Okay, we'll come to more questions in a bit when we do some examples then. Here's another example of a structure, which is actually very similar to the structure I have here. It's a simply supported beam with a load in the middle out here and a moment. Let me see if I can get it to bend the right way. So something like this. Right? So what we are doing here is we have this beam or we have this structure. There are two external loads in this case. One is a point load P acting here, and one is an end moment M acting here. Both of them are being applied extremely slowly, in the same way that we did for the spring mass system. Now, as I apply these loads, what would be the external work done by this P? What would be the external work done by this load P as it moves through delta 1? So P1, when it moves through by delta 1, what would be the external work done? Say that again?
P times delta over 2.
Yeah, P1 times delta 1 over 2, or basically half times P times delta, right? No matter what type of external load you have, external load would be half times P times delta. And the exact same thing, so I'll add that term first here, half times P1 times delta 1. And of course, M1 will also do some work. So when I go through P1 to delta 1 and M1 to theta 1, both of them do work. What is the work done by this moment as it goes through a rotation of theta 1? Right, anyone? Good. That's right. So just like force times distance is work, moment times rotation is also work. Right? So half times M1 times theta 1, that's the external work done by this P1 and M1 if they are both applied simultaneously and slowly. And just like the previous case, when I had P1 and P2, doesn't matter in which order I apply. Let's say I apply P1 first, reaches this point, and during that point M1 is constant, and then I apply M1 during which P1 is constant. That's an alternate path to the same point. Even in this case, the total work done, the total external work done by these two, I guess this force and this moment will still be the same. The total amount would still be the same, but the individual contributions would be different. Okay. You can again pick out any which way you want to load it up. You could, let me undo that. So 3, 4, or infinitely many different paths of loading. In all cases, external work done, the total external work done would be half P1 delta 1 plus half M1 theta 1. And all of that external work, as we do that external work, is going to be stored as bending energy within the beam. The beam cannot, well, at least in this case, the beam does not have any axial forces within itself. And we are neglecting the shear deformations. So the only way that a beam can store energy within itself is bending energy. When I leave it, it comes back straight. Right? So bending energy is the only way that that this beam can store energy. So let's try to see that what would that bending energy what would that bending energy stored in the beam would be. And one way to look at that is is through this curve of moment. And what is d theta over dx? What is d theta over dx? Curvature. Yeah, so moment versus curvature. If I look at moment curvature diagram of a section of the beam, so pick any section anywhere along the beam. I have this beam. It actually has infinitely many sections in there. But if I pick a small delta x section in there and in its deformed configuration, something like that, then any two sections might be doing a little bit of bending, something like this, right? Um, can this particular beam do this? This is shear deformation. We are neglecting shear deformation, right? Can it do this? It can do this, but in this case, right now, there's no horizontal forces. So once again, the axial energy stored is not something that we're considering. But bending energy means two adjacent cross sections deforming or bending like that. So if I look at some delta x section, I have a rotation theta x here, theta or at x plus delta x here. A moment is slightly different at x and x plus delta x. Using this, I can calculate what would be the energy stored in this section, and that would be half times m and d theta dx. Just like for the spring, it was half times p, the internal force in the spring, half times p times delta. And if you substitute the stiffness there, then it becomes k delta square. We'll do that here as well. Exactly the same way, the internal energy stored within a section of a beam is half times m times d theta over dx. But that is only within that section. If I want to calculate the total energy stored in the entire beam, what do I do? What do I do? How did I calculate the total energy stored in a truss? I had 7 members, so I summed it up over all the 7 members, right? For the beam, how many sections are there? Infinitely many sections. So if I want to calculate the total energy stored in the beam, I would do integration, right? So I would need to integrate this entire thing over the entire length of the beam. So dx integral 0 to L. That's the total energy stored in a beam. Total internal energy stored in a beam. How do I calculate that? Just take the bending moment diagram M, take the curvature diagram d theta over dx, which happens to be m over ei, and just integrate it over 0 to L. That's your internal energy stored in a beam. So another way of writing that is m square over ei, and m of course is a function of x, dx integral 0 to L. They both are exactly the same thing, right? Make sense? So for a spring, it is half times P times delta, or same thing for a truss member, half times N times delta. For a beam, it is half M or M times curvature and integrated over the length. Okay? So essentially, the conservation of energy principle says that this quantity up here, the total load, total external work done by the applied loads, is equal to the total internal energy stored in the beam. And if you know these two things, then you can calculate the amount of deflection or rotation using this principle of conservation of energy. And we'll do some examples about that in a little bit. Let me also talk about something related to external work and internal energy. That's probably the most important concept in this half of the course, the most important concept to understand. Very soon we'll be talking about something called the virtual work. Right now we are all talking about real external work. Very soon we'll be talking about something called virtual work, but understanding what or where that comes from is right now what I'm talking about. So I just told you that if I have a bar, if I apply load P and the bar deflects by amount delta, then the external work done by the force P on the bar is integral of P times d delta, which happens to be half P delta, right? We just talked about that. Same thing for moment. If I apply moment slowly, it goes through rotation theta. I can calculate the external work done by m and theta just as area under this triangle, and that also happens to be half m theta. Now, all that is fine, but if I had to calculate the external work done by a force in the presence of another force, which is basically a concept we will see later in principle of virtual work. But if I had to calculate the external work done by these two forces, P prime and P. So what I'm doing really here in this case is that I have this bar fixed on the left, and I'm applying P prime first. If I apply P prime first, it extends by a little bit. And then on top of that, I'm going to apply P. So total load would be P prime plus P. There are two forces. And if I were to plot the external load applied versus the deflection of this bar, I would see that when I apply P prime, it goes up to some amount, say delta prime. When I apply an additional P, it has an additional deflection of this delta. Okay, so the work done by P itself, just P alone, is still exactly the same. It is P going from here to here. This green triangle that I'm showing you, that's the work done by P alone. The yellow rectangle at the bottom, that's the work done by P prime during the process of application of P. Does that make sense? Let me try once again. So I have this bar fixed at the left end. I've applied P prime and I have deflected it to some point. Now I let P prime be there as a constant force. And on top of that P prime, I'm applying an additional P to get an additional displacement delta. So the question is, how much work does P prime do during the process of application of that additional load P? Okay, and that, since P prime remains constant during that additional deflection, that work would be this yellow triangle. Okay, when you sum up the yellow triangle and the yellow rectangle and the green triangle, that would be the total external work done by both forces, P prime and P, in going from this initial deflection to this final deflection. And later on, you'll see that this yellow rectangle is what constitutes the virtual work. This green triangle is the real external work. Okay, so this is an important concept to understand. When there is a single force acting on a structure, external work done is half times P times delta. No question about it. If there is already a force on it, P prime, and then I apply an additional force P, then the work done by P prime is P prime times delta. There's no half there. Okay, and this is a concept that you'll have to warm up to pretty quickly, because I've seen in the past people forget to put the half sometimes or put an extra half sometimes. But if you understand this concept, you cannot go wrong. Okay, so I think I'll talk about this concept again quite a few times, so maybe I'll stop that here. And the same thing happens for moment and rotation as well. If I apply a small moment m prime, that m prime corresponds to some theta. On top of that m prime, if I apply an additional moment m, and during that m, it has an additional rotation theta, then the real work done by m is this green triangle, and the work done by m prime through the application of m is m primes times theta, no half there. Okay. All right, so I think this will take Oh, maybe I should have written it here. Work done by P prime is what?
P prime times theta.
P prime times delta. So P prime times delta. Work done by the force P during this is
1/2 times P.
1/2 times P times delta. That's right. So, and the same thing for M prime times theta and half times M times theta. Okay? Question?
For work done by P,
Uh-huh.
it isn't P minus P prime times half times delta.
No, because what I'm saying is that this distance from here to here is P, right? This is
Oh,
P prime and this is P prime plus P. So this distance here is P and this base is delta. Okay. All right, so we'll come back to this concept once again when we are talking about principle of virtual work, but I thought this is a key distinction at this stage that you should understand. What is external work done by a single force P and in the presence of another force P prime. But I'll talk a little bit more about how we calculated the internal energy stored within a spring member or within an axial member. So if I have this bar now, which is being applied with this P and it undergoes some delta. So fixed at the left, I apply some load P out here and it extends by an amount delta. I want to calculate how much energy stored, how much is the energy stored in this bar. So to do that, we will uh, we will make use of the stress and strain principles. So very similar to the beam example, if you look at some small section delta x of this bar, that delta x section has some internal force which will actually be just equal to the applied load P. So N would be equal to P. That internal tension or compression would cause some stress. That stress is what I'm calling sigma. So sigma would be simply equal to the internal force N divided by the area of cross section. So that's sigma equal to N over A. And I think a couple of lectures ago, we just talked about what the average strain would be. Average strain would be the total extension, delta, divided by the original length, delta over L. And we know that stress and strain are related with the Young's modulus. Stress is equal to Young's modulus times strain. If I plug in stress equal to N over A here, and E is this, strain is delta over L, that immediately tells me that the relationship between applied load and delta can be obtained from this expression, right? If I apply some N, then I can calculate delta. If you give me delta, then I can tell you what applied force you would need to get that amount of deflection. And the external work done would still be the same, half times stress times strain, integrated over the volume, and you get all these expressions. But in this case, once again, without going through the actual algebra, you can show that I cancel off this A and this A, this L and this L. I have this half N delta. Substitute for N. What we get is, or substitute for delta, half times N square L over AE. This is an expression that I'll expect you to remember or derive it in 10-15 seconds when needed. Internal energy stored in a bar is half times N square L over AE. Okay, an alternate expression, if I substitute for delta instead, is half AE over L times delta square. So essentially what I'm saying here is, if you tell me that this bar is under an internal force N, then the internal energy stored would be half N squared L over AE. I don't need anything else. You tell me the internal force, I can tell you what the internal energy stored in the bar would be. Make sense? Or if you tell me that this bar has deflected by an amount delta, then I can tell you again what the internal energy stored would be. It's half AE over L times delta squared. They're both equal. And this is something that we use very shortly. There is a more detailed derivation given for general three-dimensional bodies, but I won't go through go in that. For bending, we have just seen that it's half mx times d theta dx, that's the curvature, times dx, and integral 0 to L. This is something that we just derived a while ago, so I won't go through those arguments again. And sorry, I should have written that up here. Don't worry, you can correct it very easily. If I substitute for curvature as m over ei, this is the same expression that we had, m square over ei as a function of x dx integral 0 to L. Or if I substitute for this m here, that would be equal to half times ei times d theta dx square dx integral 0 to L. They're all equivalent expressions, but the only benefit of the ones that are boxed in here and the one expression boxed up here is that for a beam, if I know the bending moment diagram, if I know the m as a function of x, immediately I can calculate the internal energy stored in the beam. You tell me what the bending moment diagram of this beam is, I can tell you what the internal energy stored in the beam would be. Or if you tell me the curvature diagram, d theta over dx diagram, then I can again tell you immediately what the energy stored in this beam would be. Okay. So all these three expressions are basically equal, and some of them are more convenient to use in some situations and others. So that's why we are deriving all these three expressions. Okay. So all that we've done till now is talked about or learned about how the external work done on a structure stores internal energy in the structure for two types of structures, trusses and beams. Right? For trusses, it's half n square L over AE. And for beams, it is half m square over EI integral between 0 to L. Again, don't memorize these expressions. There will be a lot of expressions to try to memorize them. But if you understand them, you don't need to memorize anything. You can pretty much derive them straight away from half P delta or half M theta. You can derive them in 15-30 seconds whenever needed, whichever one is needed. Okay, so try to understand where they're coming from. All right. Finally, there is this principle that that I want to talk about, and hopefully Dr. Liu will get to do this exercise since we have just about 15 minutes left here. The principle is basically what I've just been saying all along, that external work done on a structure is equal to the internal energy stored. We can use this principle to solve for some unknown displacement. Here's an example. I have a cantilever beam. I apply a load P here. It deflects by delta. And this is the bending moment diagram for it. So using this principle of real work and real energy, can I calculate that delta? What would be the external work done by this P when it goes through this delta? Say that again. That's right. It's always 1/2 P delta. If we are talking about real work, real energy, 1/2 P delta is always the external work done. And what would be the internal energy stored in this cantilever beam if this is the bending moment diagram? What expression should I use to calculate the internal energy stored in that beam? Maybe I'll put those expressions up here. So which one should I use? Should I use this one or this one or this one? 1, 2, or 3? 2, right? I know what the bending moment diagram is. I don't need anything else. There's EI, let's say it's constant. I can do integration so I can find the internal energy stored. So indeed, we'll use that, m square over EI times dx and integrated. So m in this case happens to be P L minus x. I'll square that. This is m square over EI, and half is also sitting out there. Integral 0 to L dx. If I expand that, I can pull out half P square over EI from the integral, and what I get is integral 0 to L of L square minus 2xL plus x square dx. Sorry, I'm scribbling here a little bit. And then if I integrate that, I would get half times P square EI. Integral of L square would be L square x minus 2x square L over 2 plus x cube over 3 between 0 to L. And if you calculate that out, it should come out to this P square L cube over 6 EI. Okay. What should I do now? I want to find this delta. Right. Just equate the external work WE to the internal energy stored in the beam. So if I equate half P delta to this, I should be able to calculate delta, which indeed, if I write that in this manner, P square L cube over 6 EI, and 2 over P would be here. So this P and square is gone. This 6 becomes 3, and indeed happens to be PL cube over 3 EI. Right? That's exactly what we had done with other different methods previously as well. Okay. How about a similar problem of a simply supported beam? Simply supported beam, I'm applying a moment m and theta here. I want to calculate what that theta is. Okay, so if we do that, what would be the external work done? Half m theta. All right, that's half times m times theta. What is the internal energy stored? The bending moment diagram looks like this: m over L times x. I square that. So half m square over L square times x square 1 over EI integral 0 to L dx. And if you simplify that out, it should come out to m square L over 6 EI. Again, equate these two quantities, and that should give me theta equal to ml over 3 EI. Which is also something that we did with the moment curvature method. Miles?
If you have a more complicated moment diagram, you just take the sum of different integrals.
Sum of different integrals. So I guess you're saying if there's multiple sections and different equations within each part, you always do m square. Let me go back to this one. And actually, sorry, not this one. Yeah, so no matter, where's that? And no matter how complicated bending moment diagram you have, all you need to do is to find the square of that expression and integrate it. So for example, if m is some long polynomial expression, you just take that big long polynomial expression, square it, and it would still be a polynomial expression, the square, and you just integrate it from 0 to l. Okay. Sorry. Here's a familiar problem that uh, all of you should have done in homework 1. I asked you to find delta x and delta y for this type of a truss problem. You remember that? And some of you might have used geometric arguments. Some of you might have used actually the principle of virtual work, which is all fine. Here's a way of using the real work and real energy principle to try to find delta x. I'm applying this load P, and this black structure deforms to this blue structure in that process. It goes to the right by delta x. So what would be the external work done? Yes, half times P times delta x. What about delta y? Does delta y contribute? No. Why doesn't it contribute? Because it's perpendicular to the applied load, right? So perpendicular to the applied load, it can move as much as it wants. It doesn't contribute to the external work. It's only half times applied load P times delta x. That's the external load. The internal work, how would I calculate that internal work? How would I calculate internal work? If I can find the internal forces in these truss members, that's all I need for internal work, right? We just talked about how half n square L over AE was the internal work. So if I can show, well, you can show it to your, convince yourself, the internal force in this member would be 3 over 5 P. Tension or compression? Tension. So I'm going to write that as a positive 3 over 5 P. This guy would be a negative 4 over 5 P, which means compression. Okay, and you can do that just by dividing this applied load into these two parts, and you will see that yes, indeed this guy would cause a 4 by 5 compression and a 3 by 5 tension here. Okay. So if I know these are the internal forces in these truss members, then I should be able to calculate the internal energy stored, which should be half times 3 over 5 P square L, which is 3 meters, over AE, plus half times minus 4 over 5 P square L, which is 4 meters, and divided by AE. And I won't go through the simplification, but you can verify that all of this turns out to be 91 over 25 P square over 2 AE, and that gives us the exact same answer that we got using either geometric arguments or principle of virtual work or any other method. Okay, so that's sort of the beauty of this principle of real work and real energy. And essentially, idea is if you have one force and you want to find the displacement due to that force in that same direction, then you can use this principle. Okay, we don't have too much time, Hui, but if you want to go through your example, I'll put up that example. So maybe let's take 2 minutes in your groups of 4 to try to decide how you would try to find, let me see.